for example 8, we have another integration problem. It's still another rational function, but notice the difference between this one and what came before it. Is this thing of the form du over u, which is what we expect whenever we're doing partial fraction decomposition. That's not PDF, portable document format. Partial fraction decomposition. Okay, anyway, and I know that because if the bottom here was an x squared plus 2x plus 17 as your u, du would be equal to 2x plus 2 dx, and that's an extreme problem. You're not going to be able to fix a missing x. The partial fraction decomposition allowed us to do that by just rewriting this as a series of individual fractions. This one, not so much. Okay, so there's got to be a different way. There's going to be something else that we could possibly do, which is going to lead us into the second objective. So think about for a second. Is there an antiderivative that, let's say we're starting with some kind of rational function, like what we have here, but the difference of the degrees in the top and the bottom, it's not 1, but it's a difference of 2. It's like this, like you have not linear, but constant over quadratic. Looks like this. Let's say I had the antiderivative of a dx over 1 plus x squared. Remember what that antiderivative is? This one is the arctangent of x, and then, hey, plus c there, right? So that's exactly what we want to try to apply in this one. But in order to get it to look like this, we're going to have to fix the quadratic that's on the bottom. And the way that I'm going to fix it is with completing the square. So I'm going to turn this quadratic into something that's going to look more like this by completing the square on that thing. So let's give that a try. I'm going to need some more space, so just take my word for it. So just with the integrand right there, I'm going to complete the square just separately. X squared plus 2x plus 17. So we only complete the square again on the quadratic and the variable parts. And we're just going to push the 17 off to the side. So this is going to be an x squared plus 2x. Group these things up. Plus a blank, minus a blank, and then here's our final plus 17. And then here's our fancy 0 to keep this thing balanced out. Completing the square, we take half of that middle term there, which is going to be a 1. We square that guy and we get a 1. So I only added a 1. To keep this balanced, I'm going to have to subtract that 1. And now rewrite this. It is an x plus 1 quantity squared, and then plus 16 when I combine these two things together. All right, then. Now I'm going to rewrite my integrand like this. So I have the integral of a dx, yeah, it's just a dx, come on, over, and then if you want to reverse in the order of this, 16 plus an x plus 1 squared. Okay. All right, now it doesn't exactly look like this here because first of all, that is a 1, and here I have it to be a 16. But that's okay. I can divide everything by 16, and I can fix that. So that's what I'm going to do next. I'm going to divide this by 16. As long as I divide the bottom by 16, that's a 16, and that's a 16, we're good to go. So now this becomes integral of 1/16, and if you want to, you can bring that 1/16 on the outside of this thing, like this, 1/16. Come on, right, pen. There we go. Of a dx over 1 now, plus, I have x plus 1 squared over 16. I'm going to rewrite this squared term right here, because I can bring this 16 into this square. If I take its square root, it's right, it's just 4 squared. And then make this as one complete term, which is squared. So I have 1 over 16 integral dx of 1 plus the quantity x plus 1 over 4, and then squared. Now it does mimic this right here, where our x is actually this. It's basically a composite function. Oh, it's a composite function, which means that I need to use u substitution on it, where our u should be equal to an x plus 1 over 4, and your du is just going to be 1/4 dx. All right, I don't have a 1/4 in there. Actually, I kind of did with this 1/16, but I've already taken it out, so I'm just going to commit to it. 1/4, I'll cram that in here, and then compensate with a times 4 on the outside of this. And then it's ready to go. As a matter of fact, I'm going to rewrite it in terms of some u's to make it more plain. The 4 times the 1/16 makes 1/4 on the outside of this integral. 1/4 dx becomes our du, and 1 sticks around, plus this x plus 1 over 4 squared becomes u squared. And now I can see that it exactly matches up with this antiderivative rule for the arctangent. So our final answer here for the definite integral is 1/4 arctangent of the quantity. What was the u? It was x plus 1 over 4, and then finally plus c. So this is the process that we are going to try to wrap our heads around for the second objective. Specifically, what we're trying to do is be able to integrate these complicated rational functions by completing the square, and this is happening when I don't have a du over u like we saw here. Instead, the difference between these is a quadratic.